All right, so we're going to continue talking on about odd and even multiplicities. The main kind of summary idea that we established from the first introductory example is that if the graph crosses the x-axis at a certain point, that corresponds with odd multiplicities, where if the graph kind of bounces, more specifically if it touches but doesn't cross the x-axis, then that corresponds to an even multiplicity. So crosses is odd, bounces is even. Okay, so in this example, we want to go through and find every zero, state each zero, state whether the multiplicity is odd or even, and whether we're seeing a cross or a bounce at that location. So first off, I want you to think to yourself, how many zeros does this graph have? Well, another way to ask that is how many x-intercepts. Remember, each zero is going to correspond to an x-intercept. So how many x-intercepts do we see? 1, 2, 3, 4. -2, -1, 0, and 2. So we're going to list all of these here in our table as ordered pairs. So there's my 4 zeros, aka my 4 x-intercepts. All right, what's happening at each one of these? What effect is this? Are we seeing a cross or a bounce, which is then going to tell us what kind of multiplicity do we have? Well, at -2, the graph is just crossing right on through. Just like normal, it just passes through that point. So that's a cross. At -1, this does not cross here. It hits at -1 and then kind of bounces back up and stays on that same side of the x-axis. So we'll call that a bounce. 0, normal cross through. And at 2, this one does cross through the x-axis. It starts on this side and ends up on this side. So this is a cross, but it's a little bit different than these two crosses here because it's also got this bend to it. So I'm going to kind of note that. Cross with a bend there. Okay, what multiplicity does that mean each of these have? Well, all the ones where it crosses have odd multiplicities. So here, here, and here are all odd multiplicities. Where I had a bounce at -1, that's an even multiplicity. But what made this one different? Well, remember in our earlier exploration, we said when something had a multiplicity that was higher than 1, like 3, 5, 7, etc., that's where we see a cross with a bend. So that means that this one probably has a multiplicity that's like 3 or 5 or something of a higher exponent there, whereas these probably were just odd with a multiplicity of 1, since it just normally crossed on through. All right. Well, if we want to write my equation in factored form now to try and create the polynomial, something that looks like this up here, we're going to need to know these multiplicities, and we want them to add up to a minimum degree of 7, it says here. Well, in order for that to happen, I've got a multiplicity of 3, 1, another 1, 3, 4, 5, 6, 7. That would add up to a degree of 7 here, which is what we're trying to correspond to. I'll talk more about that degree once we've got our actual factors written out here at the end. Remember in our earlier example, as we talked through here, that the x-intercepts corresponded over here to factors. -1 corresponded to the factor x plus 1. +2 corresponded to x minus 2. +4 to x minus 4. So down here, -2 will have a factor of x plus 2. -1, factor of x plus 1. +2 will have a factor of x minus 2. And 0 is kind of interesting. 0, you could basically write it as x minus 0, but that's just the same as saying x. So that's going to be the factor that corresponds here. Essentially, we're writing all of these as x minus whatever 0 we're working with. X minus a negative would turn positive. So I'm going to start my equation by saying f of x. Then I'll say x plus 2 for my first factor. X plus 1 for my next factor. X minus 0, aka just x. And then x minus 2 for my last factor. And just because this is kind of our habit, because we have just a normal x in here as a factor, we're most often going to see that up at the front of our polynomials, almost like it's a GCF rather than somewhere randomly within the list. All right, we're not quite done because we have to add in our multiplicities here. Any of these that we've established that have a multiplicity of 1, I don't need to put an exponent on. So x would just stay multiplicity of 1, invisible exponent of 1. X plus 2, multiplicity of 1, would have just a regular exponent of invisible 1. X plus 1, I need to have an even multiplicity. So I'm going to add an exponent of 2 so that there's 2 copies of x plus 1 and an even multiplicity. And then x minus 2 corresponded to this 0. It's going to need an exponent of 3 or 5 or 7. I'm going to choose 3 so that it will have this crossing and bending effect on the graph. Now let's check our minimum degree. If you think about multiplying this all out, there's 2 copies of this, 3 copies of this. So if I multiplied it all together, x minus 2 3 times would get me an x cubed as my leading term. An x squared would come out of here. Together that would be x to the 5th. Times another x would be x to the 6th. Times another x would be x to the 7th. So I would end up with degree 7. And the other way you can check that is just to add your multiplicities up. 3 plus 2 plus 1 plus 1 would get me also to 7. So that's how I can write this equation in factored form.